So today I'm going to present our measurement study of Google Play. Android is well over popular. More than 1 million Android devices are activated every day. Android dominates the smartphone market. Over 1 billion Android devices have been activated so far. And since Android is increasingly popular, Google Play is too. Because most of users get their app from Google Play. There is over 25 billion downloads as 2012, and now there is more than 50 billion app download. Uploading applications to the Google Play Store is easy. All you need is $25 for a developer account, and then you can upload all the apps that you want. Uploaded applications are immediately available to a huge user base, and there is no review process. So who knows what is really getting uploaded? Once installed, applications have full access to users' private life. Permission checks are ineffective since users just press OK when prompted with the permission request dialog. And despite Google Play popularity and the risk associated with downloading applications, very little is known on an aggregate level. Which is why we conducted the first large-scale and broad-scope measurement study of Google Play. We built a tool, Playdrone, to answer many questions. For example, how does Google Play content evolve over time? How many apps are clones of other apps? How do ratings correlate to popularity? How does native experience correlate with popularity? Do developers protect their secrets? How many apps have their code obfuscated? And we address many more questions in the paper. But for the rest of the talk, I will focus on the 3 highlighted questions due to lack of time. Before answering those questions, let me introduce to you the Playdrone tool we built. Playdrone is fast. It can crawl the Google Play market on a daily basis. It's a distributed system which scales horizontally. It's simple. It's just 2,000 lines of Ruby. It is versatile. It provides an extensible analysis framework and a search engine. It decompiles applications and tracks their sources over time. So how does Playdrone work in a nutshell? First, we need to interface with the Google Play API at scale. Then we must be able to discover as many apps as possible and download their binaries. And finally, we want to decompile the application sources, do some analysis, and index the results. So let's look at the architecture in depth. So the first thing we need to do is to communicate with Google Play through their internal API, which is used by the Android devices. You can think of this API as just a couple of HTTP endpoints. We use this API to, 1, discover a new application by searching for words from a dictionary, 2, fetch the app's metadata, such as ratings and download counts, and 3, download their binaries. Each request to the Google Play Store is run within a job. There is 1 job per request. We use this approach for 2 things. First, to be failure tolerant. For example, when a request fails because of network issue or because Google's backend is failing, the jobs are retried with an exponential backoff. Second, jobs are also useful to distribute the workload within the Playdrone distributed system. We leverage Sidekiq as a job scheduler, the gold standard in the Ruby ecosystem. Sidekiq makes it very easy. It handles retries, distribution, and error reporting. Sidekiq uses Redis to process job queues. Redis is an in-memory key value store. We use Redis for other bookkeeping purposes, for example, to manage our storage layer. Our storage layer is very simple. Because we want to track application changes over time, including sources, we leverage the Git reversion control system. When we discover a new application through the Google Play API, we check if we've already seen it by checking in Redis. If it's a new app we've never seen, a random server in the cluster is assigned for that application. Each application is stored in Git, in a Git repository on the local storage on the machine in the cluster. We do not use any distributed file system or NAS or other cloud solution for 2 reasons. First, it's much simpler to manage and deploy. And second, accessing a Git repository typically requires many system calls to the file system. Going through the network would kill performance. As a matter of fact, the application processing logic is directly performed on the machine that owns the corresponding Git repository. So there is no network overhead when processing an application. The processing logic includes decompiling sources, which is easy to do, as Android applications are mostly Java. While we process application, we index application sources and metadata in Elasticsearch. It's a real-time distributed analytics engine. Elasticsearch does not store the application binaries. It only stores the data on which we want to do fast searches and aggregates. And since we store the raw data in Git, including all the Google Play API responses, the data in Elasticsearch can always be regenerated. And, and this is useful in two cases. One, if you have a new question about the market you want to answer, you might need some additional analysis. Second, if you made a mistake in your analysis code, well, you can regenerate all the indexes from day one. So this is, so this is good. And to make the whole system easy to use, we provide a Rails front end to see some results. So here's an example of the Gmail app in the web interface. On the top, you can see the git clone URL, which is useful to inspect the application manually. And then you can see the what's new section, which relates on the latest update, which and then third, you can see the what's really new section, which shows a git diff of the latest update. And in this case, we saw Google rolling out new advertising features, which were actually dormant for a while. We deployed Playdrawn on 10 servers and performed 2 crawls, one in spring 2013 and one in November 2013. To give you a sense of how Playdrawn behave on a daily basis, here is a graph that shows the Google Play API throughput during a day in May. In the morning, from 4 a.m. to 10 a.m., Playdrawn refreshes the metadata of known applications at a rate of 50 requests per second. In the afternoon, from 12 to 8, it discovers new applications by performing more than 1 million word search with a throughput ranging from 150 to 250 requests per second. In total, more than 5 million API calls are made throughout the day. It generates around 100 gigabytes of network traffic just in API calls. So now that I've introduced Playdrawn, let's tackle the first question. Question number 1, how does Google Play content evolve over time? Here's a table that shows the number of free and paid applications on the market on June 22nd and November 30th. In 5 months, we noticed a 25% growth in the number of total applications, going from 90,000 apps to 1.1 million apps. And if we take a closer look at what comes in and out on a daily basis, this is what we get. The x-axis goes from April 27 to November 30th. Missing bars are due to lack of crawling. On the y-axis, you can see the number of apps that were added, removed, and updated. Some days, more than 4,000 applications are added on the market. Sometimes more than 4,000 apps are removed from the market. We were actually surprised to see that Google cleans up the market every day. And on average, the market grows by 2,000 apps daily. But not all of them get popular. This log graph shows the number of applications per download count bracket. Apps with fewer than 500 downloads account for roughly 50% of the market. And if we take the top 1% of the most downloaded applications, they account for over 80% of the total downloads. Getting an application popular is pretty difficult. One may ask, how do ratings correlate to popularity? User can rate applications from 1 to 5 stars. For each app, we take its average rating, which is a real number between 1 and 5. And we put all those apps in their respective download bucket, and then we do the average. So this graph shows the average of the average rating per download count. We see that the average range from roughly 4 to 4.5. Free applications with few downloads are fairly highly rated, probably due to friends and family that are nice. But remember that they represent nearly half of the market. After the 1,000 download mark, applications rating increase with popularity. It's interesting to note that the average rating of paid app raises quicker. Now, if we look at the maximum average rating for each download bucket, we see something interesting. The more popular an app is, the harder it is to maintain a high average rating, which is fairly intuitive. We were surprised to see that the ratings don't converge quicker with respect to the download counts. Now, if we look at the minimum average rating, it gets more interesting. It grows as applications get popular, but as you can see, there is an application with more than 1 million downloads that have an average rating of 1.6. This is super low. So we got interested in the apps that have extreme ratings like this. So here's the top 5 of the best rated applications with more than 1 million downloads. 3 of them are about the Quran. So we looked at comments of users that were rating these apps, and we find that despite that the applications were not necessarily working on their devices, or like the audio wasn't working, it wasn't displaying properly, they would still put 5 stars. And that's, so we think that the users are actually rating the content rather than the applications. Then we have some Russian applications that teach you how to get you up to speed on the driving license. Apparently it's pretty good. And then we have Slot Deluxe, Slot Machine, which is some arcade game like Vegas sort of things. And you can see that there's a huge number of ratings. So I've looked at the game and I haven't found any dialogues that pops that says, hey, please rate us on the market. So maybe it's really good. I don't know. Don't try it. It's really addictive. Then this is the top 5 worst rated apps with more than 1 million downloads. So on top, we have Wet Lesbian. I haven't looked at it, so I don't know why it's bad. I would leave you the pleasure to see it for yourself. Then we have Amoeba, which is a Japanese blogging app. So I don't understand Japanese, so I don't really know why it's that bad. Then the 2 next, HRS app, a hotel booking app, and T-Mobile More For Me. These 2 apps come pre-installed on certain devices, and users were really sad because they couldn't uninstall them. And so this is why they get such a low rating. So this sort of behavior hurts the brand more than anything else. And then finally, we have Droid Scale, which is fairly interesting. So this is the Droid Scale description page. So as you can see, transform your phone into a little balance. You can put objects and it will tell you their weight. We thought that was a little suspicious. So we git clone the repository, and here's what we get. On the left, you can see the file structure with resources and source code, the Java files. By the way, there is more code for just the advertisements than the actual application. This is interesting. And then on the right, we have the code. So on the top, you can see that it's initializing a random number generator. And then it hooks the onTouch callback so that whenever there's something going on the screen, it runs this code. And it actually picks a random number, displays it, and then it calls a method fluctuate weights that actually makes the display kind of fuzzy, and so it's imprecise, so it looks a bit more credible. So yeah, so we thought that was funny. And remember that this guy has more than 1 million downloads. And the developer actually released an ad-free version for $1, and he got more than 1,000 downloads. So yeah, this is amazing. So now that you can see that we can go in the sources, let's go to the third question. Do developers protect their secrets? I'm sure you know the answer to this one. But before, let's talk about auth tokens. They're like username and passwords, but for services. For example, they're used to authenticate a third-party application like Airbnb or Yelp to a service provider such as Facebook. Depending on the service, you may be able to do certain things. So for example, with a root-level Amazon AWS token, you may access and launch EC2 servers. With a Facebook token, you may access users' private information and write on their walls. Here's a screenshot of source file belonging to an application with more than 1 million downloads. It's common to see a single file, usually called constant.java, where all the secrets reside. So in this file, there's around 10 credentials for Facebook, Google Reader, Google+, LinkedIn, Twitter, and some other that I've never heard of. So we started to see patterns. We wrote regular expression matchers for each of the service provider to fish for auth tokens. Note that additional criteria apply to reduce false positives. But we also have false negatives. For example, if you take the Instagram application, a very popular application, they used to store their tokens in their native library. So our tool wouldn't find it. Another example is Yelp. Here's what they used to do. They base64 encode their secrets, and then they reverse the string. So anyway, we're not perfect, and we have false negatives. Here are the results. Thousands of tokens found from 9 different services. The total candidate column denotes the number of tokens found, and while the unique candidate column shows the number of unique tokens found. For example, with Amazon, we found 300 tokens in 1,200 apps. The reason for such discrepancy is because developers embed tokens in SDKs and libraries. We validated all these tokens one by one by calling a private API on the respective service. The hit rate was around 95%. And this is a huge problem for security and privacy concern. So what can be done to alleviate this issue? To illustrate one solution that we thought was interesting, let's compare Facebook and Twitter. So developers often use libraries to access services, such as the Facebook SDK to access Facebook, or Twitter4j, which is a Java library for Twitter. It's an unofficial library. And Playdrawn detects libraries in applications. So we've seen that roughly 100,000 applications integrate with Facebook, but we only find 500 tokens. A lot less applications integrate with Twitter, but we found 10 times more tokens. So why is that? The reason is Facebook relies on their SDK to authenticate third-party applications through their Android Facebook app by using Android intents. So essentially, they're relying on the OS mechanism. On the other hand, Twitter encourages developers to embed their secrets in their applications. This is a screenshot from the official Twitter documentation page. So this page is no longer accessible, and we might have something to do with that. So actually, we notified all the service providers and worked with them. Since then, all the high-risk tokens has been disabled. Services had different reaction to address this issue. So for example, Amazon notified all their developers at risk and then worked with them to resolve the issue. Facebook took a drastic measure. They invalidated all the tokens, and then, only then, after, they notified developers. So that was funny because we noticed the Airbnb applications, which has more than 1 million downloads, by the way, getting updated within hours after we send the exposed tokens to Facebook. We also work with Google. We provided Google with the Playdrawn token finder mechanism. Google has integrated this mechanism into Bouncer, which automatically scans applications and notifies developers. Here's an email that one of my friends received 3 weeks ago from Google. You can see subject action required exposed credentials. The email mentioned that an Amazon token has been found in one of his apps. So Google is definitely taking this seriously. To conclude, we made the first large-scale, broad-scope study of Google Play. We built a tool, Playdrawn, to provide answers to many interesting questions. And we made the Google Play Store a safe place. You can find all the sources on GitHub, and you can contact me on Twitter or via email. Thank you, and I will now take questions.